So, my friends, now we begin. I need to arrange this. Yes. What I'm going to do today. In my notes, the first part, the second part is actually ready. I will send this part to you. You have part of it. Several more pages and it is all. But the first part, as far as I remember, it is called Lie groups and Lie algebras. And actually I have everything I need from this part already. But in my notes there are several more results. Some of them are given with proofs, or maybe with some hints for proofs. One of them is given with a whole proof. And since we don't need this, I do not care much about the proofs. I will explain several results, more precisely 4 results from this theory, and if I am able to do this today, then this means that next time we can begin with something else. So, the problem number 1, and this is fully done in my notes. If you have a Lie group and you have a Lie algebra, and some subalgebra with Lie algebra. Everything is real or complex. I do not want to consider more complicated fields. So we have a subalgebra of a Lie algebra. Now a stupid question. It is stupid because it has an immediate negative answer. A stupid question. Is it true that this subalgebra of this Lie algebra actually is the Lie algebra of some subgroup of the given Lie group? You understand? And this depends on the definitions. But our definition of a Lie subgroup. First of all, this should be a submanifold of our Lie group. And there exists a very much immediate example, counterexample to the statement which could be done. Nobody ever considers any other example. And then I will explain to you why. You have a torus, better dimension 2. Just dimension, it can be any dimension, but to make it more clear, dimension 2. Its Lie algebra, it's commit 2 group, if you don't know. So its Lie algebra is simply the usual plane with 0 commutator. A subalgebra is any subspace of this plane. What's subspace of the plane? This is a line, right? A line in this plane. And if this line has irrational slope, then certainly it is a very good subgroup of the Lie group of the plane. But then project it onto the torus, you will have something which may be called, I'm not sure, toral winding. So such a curve which goes around the torus never stops, and as a subset of the torus, it is a dense set, right? And you prefer to say that this is not a subgroup, which gives an immediate counterexample to a possible statement. My goal is to explain to you that basically there are no other examples. This word basically certainly is not formal. But still, I will explain to you what I mean. So my first subject, I consider a Lie subalgebra of the Lie algebra of some Lie group, and I want to understand how much is it possible that it is not a Lie algebra of some Lie group. Is clear? The first statement, which basically we have, that there exists, so again, my assumption that we have a Lie group, certainly it is G, what else? We have the corresponding Lie algebra, and we have a subalgebra H, Then there is a subgroup of H which is not closed, but I prefer to use the term a virtual Lie subgroup. Meaning what? That there is a very good Lie group, H, and still better, so this is Lie group, a homomorphism of H into G, which is very much smooth. Moreover, it should be a one-to-one. One-to-one, as people say in differential topology, one-to-one immersion. So it is local diffeomorphism. However, it is not an embedding because of this crazy example of a toral winding. No questions? So first I want virtual subgroups in some respect are not worse than actual subgroups. So the difference is that H, the image of H in F is not closed in general. So still, if you have such a thing, then the Lie algebra of H is embedded in the Lie algebra of G. Because locally it is an embedding. Some neighborhood of the identity in H is embedded into G, and this provides its differential is a map between tangent spaces, which is a Lie algebra homomorphism. And it is one-to-one because the map is locally one-to-one. It's globally one-to-one, but locally also. A virtual Lie subgroup, this toral winding is an example. And now I want to say two things. Thing number one, that if you have a subalgebra of Lie subalgebra of a Lie algebra of a group, then it is the Lie algebra of a certain virtual Lie subgroup. Statement number one. Statement number two, certainly it is known to you. We discussed it. Context. Look, so statement is, so there exists a virtual Lie subgroup. I can write this in this way because actually it is an embedding from the point of view of sets. Such that Lie H is H. Now, how to do it? This is the remaining part of the blackboard is my group. This is E. This is H. Then I apply to this H left translations. And I get a family of planes of one dimension, which we call the distribution. We already use the fact that this distribution is integrable. Follows from the Frobenius criterion, and we discussed it. So there exists locally a family of integral surfaces, right? If you wish, by the reasons also discussed, it is a local subgroup. That is, if this small piece of surface contains G1, G2, and their product, then if this contains G1, so locally G1, G2, locally it is closed with respect to the multiplication. Now, how to globalize it? And we know how to do it. First, we introduce a crazy topology in G. This crazy topology is such that open sets are open sets in the integral, well, basis of for topology, open sets, basic open sets are open sets in these integral surfaces. Such a crazy topology which makes G a manifold of dimension equal to the dimension of H. Unfortunately, necessary axioms of manifolds like countability, the first, and second, Hausdorffness do not hold. Hausdorff is okay probably. countability doesn't hold. So this is not a manifold. And then we do what we did once. We consider this crazy topology, and then take the point E and take, with respect to this topology, the path component of E. Path component of E. And this will be a virtual subgroup. With respect to this topology, which we consider now, it is a Lie group. This path component, and it is embedded into G. This embedding is a local diffeomorphism. Certainly, you need to make something more precise, but this construction works. Questions? You have obviously questions there, please. No?
I was just wondering how you would show that it's second countable. You said you don't have to go.
You know, Dale, what I can say about you? There's always somebody dangerous in class who asks questions which this lecturer wants to avoid. Thank you for this. Certainly, second countability provides some problem. You see, there are basic open sets. So take an open set here and all its images. Then if you have a point in this path component, it's in path component, so it can be joined to E by a path. This path is covered by these sets, and you can find finitely many, right? So we consider the following set. First, this set. It is very much second countable because it is just a open disk in space. Then consider all points which can be reached within two intersecting sets like this. All these sets are images, translation images of this. Now we consider those sets which translated, which have intersection with this, and every intersection. Union. And so points which can be joined to my point by a path which is contained fully in two such sets. And this is actually a countable union of open sets. You can, if you consider all these, all translations, it is uncountable. But you can take translations which take E into points in this set, which form a dense countable subset. By this way, you will prove that this also is a countable union of open sets. Then you use usually the obvious induction. Take points which are joined with this by path which hits 3, which is covered by 3 neighborhoods, 4, 5, and so on. And then you will have a countable union of countable sets, and it will be countable. So it's possible to prove it. This is a proof, actually, what I said. Well, but thank you for your question. And this is a Lie group which is embedded, locally diffeomorphic embedded in G, so it is a virtual subgroup. So this is okay. So some things are true, that every Lie subgroup belongs to some virtual Lie subgroup or belongs to some local Lie subgroup. Both are true. But again, this example of yours with Thorvald Weinig shows that we cannot get rid of this undesirable adjective virtual. How to do that? And here I want to outline some results in this respect. So again, I suppose that we have G, we have H, G, and H is a virtual subgroup. Why is it bad? It's not closed. What to do with a closed, not closed set to make it closed? Take a closure. So take the closure H bar, which is also known as H super M. A closure of a subgroup is a subgroup. This has no doubts. But it is closed because closures are always closed. So this is, according to the known theorem, it is a Lie subgroup, right? So there is a subgroup. In the case of torus and toral binding, this will be the whole torus. Now we do the following. This HM is a Lie subgroup of G. So it has a Lie algebra. Actually, this M is called Maltsev closure. And this M is the first letter of his name. So for every Lie subalgebra of the Lie algebra of G, we have some bigger Lie algebra which contains that, which is the smallest possible Lie subalgebra of G, which does correspond to some Lie subgroup. Okay? And here comes a lemma, which I will not prove, but the proof is fully given in my notes. That, you know, Lie algebras have commutator Lie subalgebras, derived algebras. So we can, for every Lie algebra, I don't remember whether we have the notation, whichever Lie algebra we have, we can consider all the commutators in this Lie algebra and take the subspace spanned by these commutators, and this will be a Lie subalgebra, an ideal, and the quotient of the Lie algebra over this ideal will be a commutative Lie algebra, a zero commutator. Need any explanations to this? It is called, I don't know why, derived algebra, and the usual notation for derivatives with prime is used for that. So we have HM prime, and we have H prime. And certainly, again, this contains this. But the lemma is that actually they are the same. This is the main lemma. The proof is a beautiful proof from elementary linear algebra. Certainly, to prove it, we need some supply of subgroups of G. So we should know for some subalgebras of the Lie algebra that they are Lie algebras of Lie groups. And this is given by some simple constructions. So this lemma I will not prove here. The proof is, well, in my notes it is a page and a half. But the nature of the proof, elementary linear algebra. It's in vector spaces, subspaces, maps which take subspace in one subspace in another subspace. So some things like this, and this will give you a proof of this lemma. So this lemma, which I'm not proving, is a crucial lemma here. Now look. Yes.
Just repeat the definition of derived subalgebra.
Derived algebra for any Lie algebra. We consider all the commutators, and then the space which is spanned with these commutators, so linear combination of commutators. And it is a subalgebra, an ideal, and the quotient is commutative. Good. Now look at our result. So our Lie algebra H is squeezed now between HM and HA prime, HM prime, because HM prime is the same as H prime. By this reason, it is contained in H. Okay? Now, this Lie algebra, HM, actually is a Lie algebra certain Lie group. There is a homomorphism. This is HM over HM prime. So we just take the projection of HM over its quotient over the commutator, right? And write Rn, meaning that this is just Euclidean space. Now, we have a theorem. First, let me formulate wrong theorem, and then you remember the right theorem. That a homomorphism between Lie algebras gives rise to a homomorphism between Lie groups. And the right thing that it is so. If, however, the Lie group is simply connected. We have no idea that HM is simply connected. Moreover, the example with torus shows that it is very much not so in general, right? How to make a Lie group which is not simply connected, how to make it simply connected. Topologists know it immediately. You take the universal cover. So, I didn't say. H, a subalgebra of this, is mapped into some subalgebra of Rn. Excuse me, what is a subalgebra of Rn? It is some Rm, right? Right? Very interesting. Now we say the following, that this map of HM into R, and actually the quotient here is over the same space. So gives rise to a Lie homomorphism. Not this, but this. So we need to take the universal cover, denoted as F. And now I say that H, the virtual subgroup, becomes, so if this is P, then H becomes the following. You should take F inverse of Rm of this and apply P to it. Here I can stop, but still. The same construction, so actually why H is not a subgroup? It is because of this projection. In HM tilde, everything is okay. We have this map, and F inverse of Rm is very much a Lie subgroup. So in the covering, actually from Rm. But now we have this projection, and when we apply this projection, then this virtual Lie subgroup, this group becomes a virtual Lie subgroup. This P makes it. This is a very much a Lie subgroup of this. This is not a Lie subgroup, but this shows that actually what happens. We have this pair actually of Lie groups. HM, I mean Roman HM, and HM prime. I didn't say this. Lie groups also have commutator subgroups. Do you think that a commutator, it is what? It is a group generated by all commutators. And it is a question to you. Do you think that when I am asked, I say yes immediately without thinking, because it is a subgroup. A commutator subgroup algebraically is a subgroup in the group. And then I say without being much convinced that is a closed subgroup in H. Then it is a Lie subgroup. However, the closeness is not so clear. What is definitely true and written in textbooks, that if the commutator subgroup is simply connected group, the commutator subgroup will simply connected group is a Lie subgroup, and it is very, very easy to prove because it is a kernel of a certain map of this group into Rm, precisely of this map. As to an arbitrary group, usually written in books, that its commutator subgroup is a virtual subgroup, virtually connected, whose commutator subgroup is virtual. Looks very strange. Looks very strange. But who knows? I don't know example, but I don't know the proof either. This, what we have? We have the group H tilde M. We have its commutator subgroup. The quotient is Rn. In this quotient, we take a subgroup which is Rm and take its inverse image. It's the same as for torus. And then you take the projection, again, the same as for torus. And you get definitely a virtual subgroup, not a subgroup. My notes contain, for this result, some full presentation. So you can read it there, and I will never return to it. Theory is beautiful. Questions? No? Yes, you have to have a question. Yes.
So can we say anything? Suppose you only know the Lie algebra. Can you say anything about what this HM is going to be, or how much bigger it will be than the original H? Is there a way to characterize? Also, is there a way to characterize subalgebras that will correspond?
Yes, it is. You see, I don't see actually any construction not involving Lie groups. No, I don't. I can say more than I said. That it will. This HM is a bigger subalgebra with the same commutator as H, and maybe this is the biggest subalgebra with the same commutator. I'm not sure, but it might be so algebraically. I think it is so, but so the maximal Lie subalgebra of G, whose commutator is the same as the commutator, whose commutator subalgebra is the same as the commutator subalgebra of H. You have a question, Dale.
Well, I was just wondering, is that unique, maximal piece of algebra that has the same commutator?
I don't need maximal. What I need a Lie algebra which is a Lie algebra of some Lie group. So I'm not sure that I need it. And maybe actually HM is smaller than that. It's very, very, very much possible. Now let me, I don't think I have 20 minutes remaining. I think that maybe the last of these 4 subjects should be considered next time, which I didn't want. The next question. Suppose that you have some finite dimensional Lie algebra. Forget about Lie groups. Do you think it is possible to embed it into some JLN? Is any finite dimensional Lie algebra isomorphic to a subalgebra of the Lie algebra of matrices? You understand? Yes, because you know it, or yes, because you sort of think it should be true?
Yes, because I know.
Yes, knowledge is I also know it. So there is a theory which is precisely this theorem, that every finite dimensional Lie algebra over, well, any field of characteristic 0, real or complex, is isomorphic to some subalgebra of, yes, the algebra of matrices. This theorem is called Ado theorem. It's the author of the theorem, 3 letters, ADO, a modest Russian mathematician. I met him once in my life. He was sort of older than I. This was his dissertation. He was very modest. He never actually realized that his theorem with his name is presented in all possible textbooks about Lie groups. Ado theorem. He taught in a modest college in Kazan, never attended any, he was invited to conferences and so on, he never attended any conference. Yes. Now this theorem, let us think, is it possible to prove it just at 1 to 3? How to embed a Lie algebra? Have a Lie algebra. It is G or H, whatever you wish. How to embed it into JLN? Very big N. Let's try to do it. There exists such a thing which is called the adjoint representation. I think I already use this name and notation here. So, a theorem. Every the algebra is isomorphic to can be embedded. I can write R or C whatever I wish here. Actually in field of which is 0. The dissertation of Adele was pure algebraic, so for him just field of which is 0 was okay. So how to prove that? We consider the adjoint representation of G in the set of all linear endomorphism of G. For xc in G, we take the transformation which takes an element eta of, again, G into the this commutator. This is called the adjoint representation, a representation of a Lie algebra in itself. So every element of a Lie algebra becomes a linear transformation. Yes. Now my question, is this really a one-to-one? Is it really a well, certainly a homomorphism that follows from the identity? It is a Lie algebra homomorphism, that's okay. But is this one-to-one, or is it center? Yes. Center of a Lie algebra, center of anything, is the subset of G, which commutes with everything. So it has 0 commutators. A center of ideal, actually commutative. Still, the algebras do have centers. And this short proof is the proof of Adel theorem, is the most important, in the most important case from the point of view of Lie theory. If G has no center, if the center is 0, which often happens, if the center is 0, then yes, this is an embedding. What to do if the center is not 0? And this is the whole proof of Adel theorem. Actually, what we need to consider, non-trivial center. And what we want to construct? We want to construct a representation of G, which is faithful. So no element of G gives rise to the 0 transformation. There are algebraic notions which help to do it. There is an infinite dimensional representation which immediately is faithful in the so-called universal Liouville algebra. Maybe we'll consider it, but now I don't want to say anything about this. However, it's infinite dimensional, but it has a lot of ideals, including ideals of finite dimension. So we need to find an ideal in the universal Liouville algebra, factorize it over this ideal, and this will be a space in which G is represented faithfully. So this is how the Adel theorem is usually proved, by including the initial proof in Adel's dissertation. All about this. If you have a question, questions? Dale? Well, Henry, your question, so you, yes.
What do you call, is there a name for this infinite dimensional representations that you use?
Universal algebra is an associative algebra,
Oh, but
and there is a representation of G in this universal simply multiplication elements of G, and certainly this follows from with PBW, but at least looks obvious. Yes, but it is infinite dimensional. Now, next question. Again, that you have some in it's Lie algebra. So, to be virtual, you need this Lie algebra is already a subalgebra of a Lie algebra of some Lie group. But we don't know anything. This Lie algebra comes from nothing. You can combine this. By the way, this will work. This will work. So if you, it follows theorem. It was actually proved much earlier than Ador's theorem. This is why you're right. If you use Ador's theorem, then we get it. Lie algebra is a subalgebra of some GLN. GLN is a Lie algebra of a Lie group. Then virtually sub. So all we did will work. But if no, simply this has a direct proof, and let me present it to you. There exists a Lie group, which is a good candidate. So we have a Lie algebra G. Let us consider the group of all automorphisms of this Lie algebra. In other words, we have a Lie algebra, self-maps, linear automorphism, which also respects the commutator. Automorphism of a Lie algebra, it is a map, a homomorphism of this Lie homomorphism of this Lie algebra into the algebra, which has an inverse. Automorphisms of a Lie algebra form a group. Obviously, this is not only for Lie algebras, it's a very general algebraic fact. But in the case of the Lie algebra, these automorphisms become actually linear self maps, linear automorphism of a vector space, right? So. The name is the third Lie theorem. I use this name if you promise not to ask me about the first two Lie theorems, which actually certainly covered by this course, but I prefer not to formulate them separately. But this is the third Lie theorem. So we have a Lie algebra G. I want to construct Lie group. I consider the group of all automorphisms of G. And this is with the usual composition operation. So this is a subalgebra of this, where subgroup, excuse me, what I said. A subgroup of this, where n is the dimension of my Lie algebra, right? it is very much, it is obviously closed. So this is Lie subgroup. It's a Lie group. Is it true that a Lie group of this Lie algebra is related somehow to my initial Lie algebra? For example, it is precisely our initial Lie algebra. Look, the Lie algebra of this Lie group is the subalgebra of this, right? So we have this Lie algebra of endomorphism and Lie algebra of this. So which endomorphisms of G are elements of the Lie algebra of this? What are infinitesimal automorphisms? And there exists in algebra such a beautiful word, derivation. It is that actually this Lie subgroup of this group, its Lie algebra is the Lie algebra of all derivations of G. What is derivation? A derivation is the map such that f of later very usual product rule is a derivation. It is very clear, prove in a second, that a tangent vector to G ln R is just a tangent to the subgroup out G, even on leaf, it is a derivation. So we have a Lie algebra of derivations of G. Is it G? Let me say something like G. There are such preferred derivations, which are called inner derivation. And inner derivation of G is the following. We take an element C in G and then consider its adjoint action, that is a map of G into G, which takes eta index C eta. And this is a derivation which is equivalent to the Jacobi identity. Right? Derivations. Since we have this correspondence for an element of a Lie algebra, we have a derivation, we have this map. And here, which is the same as this. And now we want to say that this should be an isomorphism. Yes or no? A kernel. A kernel is what? Same thing. The center of G is precisely the kernel of this map. So if G happens to have a center, then this will not work. Suppose that G has no center. I mean the Lie algebra. Is it onto?
Not necessarily.
Not necessarily. So not every derivation is inner. There are outer derivations. Do you understand where they come from? It's very obvious. Hmm? Again? I want to say that imagine that G is an ideal in some other algebra. That G is an ideal of some other algebra, say F. Then every element of F also will provide a derivation commutative with this F. And this is not inner, it is outer. Precisely because it is, well, outer because not inner. So there might be outer derivations. So two things are bad here. The existence of center. About this I cannot say anything, at least for now. And also the existence of outer derivation. This second thing is not so harmful. Because if this map is not onto, then still G becomes a subalgebra of a Lie algebra of some Lie group, this which makes it a Lie algebra again of a Lie group. The existence of center again requires some algebraic yoga. I'm not sure that we will do it here, but it is not precisely hard. So these two theorems. And now my remaining 2 minutes and a half, I can only announce the last problem, which we will shortly discuss next time. But this is really exciting. So I said 1,000,001 times here, maybe more, I didn't count, that if we have, there is a correspondence between Lie algebras and Lie groups. So we have this map, exponential map of G into G, which locally is a diffeomorphism. So in some neighborhood of the identity, it is diffeomorphism, right? Suppose that we know commutator here and don't know the multiplication here. How is it possible? Possible to find the multiplication? So actually, this multiplication, since this exponential map gives a diffeomorphism between neighborhoods of 0 in the Lie algebra and the identity in the Lie group, this means we can forget the Lie group. This means that the commutator operation in G can be somehow reworked in a local multiplication operation, right? I can say that if we have two elements, xi and eta, in G, then we can take their exponential images in G, take their product, and apply the inverse map. Locally it is defined. You can call it the logarithm if you prefer. And this, you can denote this like this. And this is a local multiplication, local group structure, actually in the Lie algebra, which should be determined somehow by the commutator. Is it possible to present this as in an explicit formula which uses only commutators in G? Do you understand the problem? Have you ever heard of this formula? This formula exists. It is very questionable that it is explicit. But it exists, and it's called Campbell-Baker-Hausdorff formula. In the way as it's presented in all textbooks, it belongs to one of my teachers, Dinkin, was approved by him in the year of 49, maybe also his student work. There is some formula for that. And I will gladly briefly discuss it with you next time. So you should see the problem, that we want to reconstruct the multiplication in the Lie group from the commutator in the Lie algebra. And this is what I will briefly show to you next time. And then we will fully forget about Lie groups and will be immersed in the algebraic theory of the algebra. Thank you. No, thank you. First, I want to return to you your works. Thank you for them.